Okay guys, assalamualaikum and good day. In this video we're going to proceed with the detail on differentiation. In the previous video I already show you the idea of what differentiation really is, where they're actually finding the difference between difference in y and difference in x divided. That is the main idea of what really happened in differentiation. Okay, it is just that we don't really want to find the difference that is that we have no problem in finding difference if we are going to find between the interval. But now because of we want to look at each point of the graph, let's say we have this graph. This is x to the power of 5, the graph of x to the power of 5. We want to find the difference at each specific point. If we to zoom in, we want to look at the difference in each of these points where the difference actually approximate close to 0. So we can't really just simply subtract between the difference of x and difference of y. So that's why we are using the concept of differentiation. Okay, so and we have learned that by using the concept of limit, they come out with one formula that can be generally used in all kind of situation, all kind of functions. However, to use that sole formula, right, might be a little bit troublesome, because in certain functions the process will be longer. Okay, so that's why mathematician came out with several preset formula that can be used directly when you encounter with certain function. Okay, so the notation that we are going to use later, right, usually dy dx, right, be clear with it, meaning that we are going to differentiate y in terms of x. So when you encounter with a formula, with an equation y equal to x, then the differentiation will be dy over dx. So it depends. If your equation is in terms of y and t, y equal to t, then your differentiation later will be dy over dt. Alright, so this is changed according to the terms in variable used in your equation. And you also have f prime x. So again, it is not always x, it depends on your equation. But prime here is the notation used when you differentiate. Okay, and this is also the term that we can use in this situation where you differentiate the function, right? But as you can see here, this is the term said d, not dy. It is actually d of the fx, right? When you have an equation of fx equal to what, right? So this is the terms, and then this is also another term that we already use this one. Okay, so let's directly look at the technique of differentiation that we have. So the preset formula for power function is this. Whenever you encounter with a function or an equation that contains power, for example this x to the power of 5 or x to the power of negative 11, we can find the derivative of it by directly applying this preset formula. So how to use this formula? So when you have x to the power of n, any n, right, just subtract, just pull down to the left side, right, the n here, you bring it down to the left side and subtract the power to 1. So you'll get like this. Okay, so if you try to practice, try to apply it, you're going to see that, okay, x5, differentiate it, you put these terms to the left of your x, you get 5, and then 5 minus 1 is 4, so 5x to the power of 4 Right. So for our first example here, why don't we try to be clear where is actually this 5x4. Remember, whenever you conduct this, what you'll get is actually the value of a slope. Okay, remember the value of a slope. So 5x4 here represents the slope of this. This is x5. This is if you try to draw a graph for x to the power of 5, this is what you get. Okay, and you're going to see that for example, if you want to find, this is the equation of your slope, sorry, just now, where you have yeah, 5x4. For example, if you try to substitute x, right? Let's say in a situation of x0, what will be the slope? Let's look at our graph. So we'll see that when x is 0, the line will lay flat like this. So we can expect that the value of slope is 0. Or if you try to draw a slope, it will be 0. When your slope, when it is 0, it will lay flat. Okay, so if I try to draw it when the x is 0, this is what I get. Okay, you're actually unable to see it because it is in line with x exists. Let's try to change a bit. How about 0.8? If you try to calculate 0.8, you get the slope value of 2.05, something like that. Okay, so 2.05, first of all, it is a positive value, so we can expect it to be the slope to be positive, which is this way, right? And let's see where is the slope. This 0.8, right, just now. So the line should be touching this curve, right? You can see it later. It should touch this curve. Okay, let's see the tangent line, which later we're going to learn about it. Right, so you have it. As you can see, this is the line, right, that represent that actually touching 0.8, and the 2.05 that being calculated when you substitute in 5x to the power of 4 is actually representing this. Just now, when you say x0, where you should get a tangent line, is actually lay flat, right? And if you can see here, 0.1, if you try to calculate it in your in the function of 5x to the power of 4, you should get a value that is so small, 0.007, meaning that when your x is 0.1, your slope is actually there. There's a small slope, right? Let's try to put 0.1. What will be the slope? Okay, it's also around there, but actually, if you try to really focus, try to zoom in, you'll see that it is not really flat. You have some sort of increment in the slope, positive increment, right? That is the idea of dy and dx, what they are looking at. For example, 0.6, you're going to see that there's a line that will be touching 0.6 just to measure the slope at the 0.6, right? See, so this is called tangent line, and we're going to learn about it later. Okay, so let's look at our next example. Maybe let's look at exercise. Okay, x. Okay, x, when you differentiate, you'll get 1. So basically, the differentiation is 1, meaning that you can't really substitute any x to find a slope. Why? Because for x, it is actually just a straight line. There is no slope, no issue here, right? So let's proceed to the next one. X negative 3. Okay, x negative 3. So you put it in front, negative 3x, negative 3 minus 1, you'll get negative 4. Alright, this is simple. Now the next one, derivative of a constant times a function. So the idea is they want us to know how to deal with a constant that is actually with a function. Okay, so differentiate the following. So how to do that, right? We have pi over 7x. First we need to determine what is the constant for this function. So pi is a constant and 7 is a constant. So we can deal with that. Okay. So now this is how we put notation to differentiate. So next, in dealing with constant, we should pull it out. Okay. Just so that it will be easier for us to differentiate later. So now, when we pull it out, this is what it becomes, right? Pi over 7 behind the differentiation. So we don't need to differentiate that. And that left us with 1 over x, or we turn it into the power function, it becomes x negative 1. Suddenly it becomes easy for us to differentiate, right? So just ignore the constant. Differentiate the power, differentiate this function using power rule, and this is what you get. Alright, let's look at the next one, derivative of sum and difference rule. Okay, so this is quite simple. Okay, how to differentiate when you encounter with summation of functions or subtraction of functions. So you basically just need to treat them separately. So you differentiate the first part first and then differentiate the second part. And these two the same. You differentiate the first part and differentiate the second part. Just a pre-algebraic revision on this set. For those who are not remember, to deal with this, right, the easy way is to convert it into power 1 over 2. Okay, or you can just look at the example, look at how they do that. Now let's try to do this one, exercise 4.3. Alright, so this is how you should do it. So differentiate each of them separately, and then to make this thing easy, we try to remove the constant, split the constant like this. Put 1 over pi outside, we put 4 outside, and there is no constant here, so we proceed. And after that, we differentiate what's inside. And lastly, this is what we should get. Now, let's try to make sense of it. So, this is the function, and this is the dy dx of the function. So, what does it mean by that? If you try to draw a graph of this function, okay, this is what you should get. This is the graph of that function. And if you try to apply the differentiation, try to apply the x value, let's say for 0.1, you will later get this kind of straight line that touching 0.1. As you can notice, this line is this way. To indicate, you should get indicate a negative trend line. In other words, when you calculate for you substitute 0.1 here, you should get negative value for curve. As if you substitute maybe 0.5 or 0.4, the line will be this way, meaning that when you calculate it using this formula, you should get a positive value. Alright, so let's try to input a bit. 0.1, right? So for 0.1, you should get this tangent line. Sorry, 0.1, you should get this tangent line, right? So negative way, right? So if you input it for maybe 0.4, the line should be the other way around, which indicate a positive value. You can try to calculate it later. Okay, so that is what really happened when you differentiate, right? So you can try to calculate everything else by yourself. In the next video, we're going to proceed with other derivative preset function. Right? Thank you.